Hello and welcome to this A-level chemistry explanation video about acids and bases. This is the first of a three-part series of videos about this topic. In this video, we'll be focusing on the definitions and reactions of acids and bases. We'll look at strong acids and how we calculate their pH, move from there into Kw and calculating the pH of strong bases, and we'll finish by looking at weak acids and cover Ka, pKa, and pH. There are actually three different definitions for acids and bases that you need to be aware of, and we're going to look at them all here. The first one is the most important one for this topic, which is the Bronsted-Lowry definition. Acids are defined as proton donors or hydrogen ion donors, and bases are defined as something that can accept hydrogen ions or protons. And then Arrhenius acids are defined as acids that ionize when you put them into water, and that means that they dissociate and they produce hydrogen ions and something else. And bases will dissociate in water to produce hydroxide ions. And then the last definition is the Lewis acidity, and you need this more in the transition metals topic, really. But a Lewis acid is defined as an electron pair acceptor, and a Lewis base is an electron pair donor. Sometimes there might only be one of these definitions being satisfied by a situation, other times it could be two, or maybe even all three. Acids and bases can both be defined as being either strong or weak. Now, this is really different to concentrated or dilute. A concentrated solution just means that there is a large amount of solute dissolved in the solvent, whereas dilute means there's not very much. Strong means something quite different, and it's a measure of how fully the substance ionizes when you place it in water. A strong acid or base will fully ionize when you put them into water. And so that means that this reaction will go to completion. In contrast, a weak acid or a weak base will only partially ionize when you put it into water. And so that means that this reaction will not go to completion and it will be reversible. If we take a look at a few examples, strong acids are the ones that you've most commonly heard about, really. So hydrochloric acid, sulfuric acid, and nitric acid. And all three of these will dissociate, they will fully ionize in water, and that means this reaction will go through to completion. Strong bases, really, for A-level chemistry, encompasses anything that contains the hydroxide ion. So sodium hydroxide, potassium hydroxide, and barium hydroxide. Again, these will fully ionize. This reaction is shown as going to completion, and the arrow that we use represents that. For a weak acid, we're really talking about anything that is a carboxylic acid, so methanoic acid, ethanoic acid, etc. Since these only partially dissociate, we show these as equilibria, and we have the double-headed arrow in the middle to represent that. And the equilibrium will lie significantly to the left-hand side here. And last of all, weak bases. These really, there aren't many that you need to know for A-level chemistry, and the two that I would suggest that you remember are ammonia, and to link it to an organic chemistry topic, anything that's containing an amine functional group is likely to be a weak base. I'm going to outline a number of the different acid reactions that you need to be aware of from across the A-level chemistry course, and I'll pull them all together here. Firstly, and most commonly, acids react with bases to make a salt and water. And this salt will take its name partly from the base. Usually it will just be what is the metal present in the base, and then the other part will come from the different acid that we might use. And so hydrochloric acid will react with sodium hydroxide to produce sodium chloride and water. And if we were to use a carboxylic acid for an example, you would have ethanoic acid perhaps reacting with potassium hydroxide, and this would turn into potassium ethanoate salt and, of course, water. Now, if the carboxylic acid had a functional group at two ends, we had something called ethane dioic acid as an example, what would happen is the sodium hydroxide, for instance, that it's reacting with would react with both of those functional groups. And this would affect the balancing of the reaction. So we'd need two sodium hydroxide, and we would put a sodium at each of those ends, and we'd end up making two water molecules as a result. Acids can also react with metal oxides. When this happens, we still make a salt and water, and I'm showing an example of the equation here. When an acid reacts with a metal carbonate of some sort, we get a characteristic effervescence or fizzing being produced, and this is down to the production of carbon dioxide gas. This is, in fact, one of the tests that you need to know. It's a test for a carbonate ion. We can add an acid to it, and that fizzing means that we have got a carbonate ion present. Not only do we make the carbon dioxide, we make the salt and water in the same way that we saw in those other equations. The last acid reaction is when acids react with metals. When this occurs, because there is nothing else with the metal, we can only make a salt and hydrogen this time. There is nothing that's got the oxygen in that can allow us to make water. So magnesium reacting with sulfuric acid would make magnesium sulfate and hydrogen. Lots of acid-base reactions can actually be considered to be equilibria. If we reduce the reaction down to simply the passing of the proton between the acid and the base, we can see this more clearly. If we take this example that I've got here, where we've got the strong acid hydrochloric acid, it is going to donate a hydrogen to the ammonia. And it can do this because the ammonia, the nitrogen in the ammonia, has got a lone pair that it can use to accept that proton. Once this has happened, we produce the ammonium ion and the chloride ion. And ammonium is actually weakly acidic. And this makes sense because it's gained an extra hydrogen and it's now an ion, and so it has the potential to donate that proton back. And this chlorine has in fact got 4 lone pairs that it could use to accept that proton, and so this reaction is reversible. The equilibrium is likely to lie heavily to the right in this particular example, but it is potentially reversible. Because of this, we need to use some language about which acid we might be referring to, because there's an acid on both sides of the equation, and the same with the base. So the initial acid, the hydrochloric acid, is simply just referred to as the acid, and the ammonia simply the base. But the acid, once it has donated a proton, is taken to be a base. We call it the conjugate base because it is the base that goes with that acid. And similarly, the ammonia accepts the proton, and once it accepts the proton, we make the conjugate acid. And literally, we would define the conjugate acid as the species that forms once the base has accepted the proton. And so, in any acid-base equilibrium, there are always 2 conjugate pairs. You can actually get this when 2 acids react together. If we take the example of sulfuric acid, concentrated sulfuric acid, reacting with concentrated nitric acid in the reaction that generates the electrophile for the electrophilic substitution of benzene. Now, it seems weird these 2 acids are reacting together, but one of them is better at donating protons than the other. And in this case, the sulfuric acid is the stronger acid. It is the better proton donor, so it will donate a proton to the nitric acid. And you can see that that's happened because in the products, we've got the HSO4-, which is what forms when the sulfuric acid loses one of its hydrogen. And the HSO4- is the conjugate base that belongs to the sulfuric acid. And we make H2NO3+, which is the conjugate acid to go with the nitric acid, which was the base in the reactants. It's a really common question in A-level chemistry to calculate the pH of a particular solution. So what actually is pH? Well, the pH of a solution depends on the hydrogen ion concentration of that solution. The symbology pH actually means hydrogen ion potency. Now, you will remember, hopefully, that the lower the pH of a solution, that tells us that the acid is stronger. You can calculate the pH of a solution by taking the negative log of the hydrogen ion concentration of that solution. This is an incredibly important equation. And in fact, if a question asks you to define pH, they really just want you to give back this really important equation that's here in the form as I've written inside the box. The calculation is log to the base 10, but we don't normally write that 10 because we assume that when we're writing log log, that's what we mean. And if we mean something else, for instance, in the kinetics topic, we write ln for natural log. Since it's in the base 10, a difference of 1 in the pH means that the hydrogen ion concentration is 10 times bigger or 10 times smaller. So even a small change can be really significant. As a consequence of this, it's really important to report pH values to 2 decimal points, because even that second decimal point can be really significant when we're working with a log scale. So any calculation that requires you to calculate the pH of a particular solution is going to finish with the equation that I'm showing here, which means that the second to last step in the process is likely to be to find the hydrogen ion concentration. A question might come at this from the different angle, though. It might give you the pH of a particular solution and require you to then calculate the hydrogen ion concentration by rearranging the pH expression. So this gives us another equation that is not quite as important as the first one, but I'd be really surprised if you didn't use it at least once on an A-level chemistry paper. And that is that the hydrogen ion concentration can be calculated by using the inverse log of the pH. And what that is written as is it's 10 to the minus pH. And so you'll have to use the shift or the second function on your calculator and then type in the negative of the pH. And so, for instance, if we had a pH of 4.25, we could work out the hydrogen ion concentration by doing 10 to the power of minus 4.25, which gets us a hydrogen ion concentration of 5.62 times 10 to the minus 5. Since strong acids fully ionize in solution, this means that the moles of acid in that solution will be the same as the moles of hydrogen ions in that solution. Or, more usefully, the acid's concentration will be the same as the hydrogen ion concentration. And you can see that in these equations that I'm showing here. The moles of hydrochloric acid and hydrogen in the equation are the same. And so that means that if I had 1 mole of hydrochloric acid, I'll make 1 mole of hydrogen ions. And if I had 2 moles of nitric acid, I'd make 2 moles of hydrogen ions. We can see that those are going to be the same. And so this means if we're asked to calculate the pH of a nitric acid solution with a concentration of 2.20 moles per decimeter cubed, then we know that the hydrogen ion concentration will also be 2.20 moles per decimeter cubed. And so the pH is simply the negative log of that number. And so negative log of 2.20 is minus 0.34 to 2 decimal points. And I use this as an example to show you that the pH can be less than 1 and in fact less than 0. We could go the other way around. We could be asked to calculate the hydrogen ion concentration for hydrochloric acid that has got a pH of 1.85. And so this means that we can find the hydrogen ion concentration by doing 10 to the power of minus 1.85, which gives us an answer of 0.014, and this means that the hydrogen ion concentration is 0.014 and the hydrochloric acid concentration will be the same. Sometimes acids might contain more than one hydrogen ion that they can donate. A good example of this is sulfuric acid, and we say that this acid is diprotic to represent the fact that there are 2 protons that it can donate. And so you can see from the dissociation equation that for every 1 mole of sulfuric acid we have, we can get 2 moles of hydrogen ions from that. And we need to keep this in mind if we're calculating the pH of this acid. So for instance, if we're asked to calculate the pH of a sulfuric acid solution that has a concentration of 1.90 moles per decimeter cubed, this means that the hydrogen ion concentration will be 3.80 moles per decimeter cubed. In other words, double. And so the pH will be negative log of 3.8 rather than 1.9. And so this means that the pH will be negative 0.58 to 2 decimal points. And we need to keep this in mind in the other direction as well. So for instance, if we're asked what is the sulfuric acid concentration, if it has a pH of 0.65, we need to first recognize that hydrogen ion concentration is 10 to the negative pH, so 10 to the negative 0.65, which gives us 0.22 for the hydrogen ion concentration. But since the moles of sulfuric acid is half of the hydrogen ion concentration, we need to divide that by 2 to give us a sulfuric acid concentration of 0.11. Questions might sometimes ask us to find the pH of a solution of pure water. And to do that, we need to use something called the ionic product of water, which is given the symbol Kw. To understand this, we need to first recognise that in pure water, a small proportion of the molecules will ionize, and it will produce hydrogen ions and hydroxide ions. This is really only a slight dissociation, and so this means that the reaction is an equilibrium, as you can see from the symbol that I'm using here. Now the Kc, the equilibrium constant using concentrations, for this expression will have the products on the top, so hydrogen ion concentration and hydroxide ion concentration, and the water concentration on the bottom. Since this dissociation is only very slight, equilibrium lies heavily to the left-hand side, this means that the water concentration before equilibrium is reached will be pretty much equivalent to the concentration of the water at equilibrium. And so we can consider the concentration of water to be a constant value. And so if we put both of our constants on the left-hand side, you can see we've got Kc multiplied by the water concentration is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration. What we do in chemistry is the same as in maths. If you've got two constants in the same position, you combine them to get one. And this is the origin of the Kw value. And so you can see that Kw is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration, which is why it's called the ionic product of water. Those are the ions that came from the water. At 298 Kelvin, the value for the ionic product of water is 1 times 10 to the minus 14 mole squared dm minus 6. You'll usually be given this value, but you'll probably do so many questions that you will end up remembering it. For pure water, we know that the pH is 7, and we can prove this by rearranging the Kw expression. If water is pure, that means that we've only got water present, so that means that for every hydrogen ion that has been produced as a result of this dissociation, we will have a hydroxide ion as well. So those two concentrations are going to be the same. And so if we take out reference to the hydroxide ion concentration then and replace it with hydrogen ion concentration, you can see that Kw is equal to H plus squared. And so as a result of that then, the square root of Kw is equal to the hydrogen ion concentration. And so the square root of 1 times 10 to the minus 14 is 1 times 10 to the minus 7. And so that's the hydrogen ion concentration for pure water at 298 Kelvin. And so if we take the negative log of this value to find the pH, what we can see is this gives us a value of 7.00. And so we've proven that at 298 Kelvin, pure water has a pH of 7. If the temperature of water changes, its pH changes as a result. And this comes down to this dissociation equilibrium. The dissociation in the forwards direction involves the breaking of a bond. Breaking of bonds is always endothermic, and so the forwards reaction for this dissociation will be endothermic. And In an equilibrium, if you, for instance, raise the temperature, the equilibrium is going to shift to decrease that temperature. And so that means it will shift in the endothermic direction, which we've just said is to the right-hand side. As a result of this shift, that means the concentration of hydrogen ions is going to increase. And we know that that means that the pH will decrease. And so you can see that this will have an effect on the hydrogen ion concentration. It will also have an effect on Kw, since Kw is the product of hydrogen ions multiplied by hydroxide ions, or for pure water, Kw is H plus squared. If the hydrogen ion concentration increases, Kw must increase as well. And so what we can say is that as temperature increases, pH will decrease, and so the pH will be less than 7 if the temperature is greater than 298 Kelvin, and Kw will be greater than 1 times 10 to the minus 14 as well. And conversely, if the temperature is below 298 Kelvin, pH will be greater than 7, and the Kw value will decrease. Even though the pH has changed, though, we're still not in a situation where we've got acidic or basic conditions. And that's because that in pure water, the hydrogen ion concentration is the same as the hydroxide ion concentration. And so that means we are effectively neutral. We haven't got one of those bigger than the other. If we've got a question, it might ask us, what is the value for Kw if the pH is, say, 6.63? And we know that Kw is H plus squared, and so what we have to do is we have to work out what that hydrogen ion concentration is first. So we do 10 to the minus 6.63. This gives us a hydrogen ion concentration of 2.34 times 10 to the minus 7. And so when we square that value, we get 5.495 times 10 to the minus 14, or 5.50 times 10 to the minus 14 to 3 significant figures. We can calculate the pH of a strong base by utilising the value and the equation for Kw, because Kw is still a constant for a given temperature, even when we're not considering pure water. So Kw is the product of the hydrogen ion concentration multiplied by the hydroxide ion concentration, which means that if we know the hydroxide ion concentration and the value for Kw, we can find the H plus concentration and then negative log that to get the pH. So for instance, what is the pH of a 0.65 moles per decimeter cubed solution of sodium hydroxide at 298 Kelvin? Well, the fact it's at 298 Kelvin tells us that we can use Kw as 1 times 10 to the minus 14. Sodium hydroxide is a strong base, so that means that the hydroxide ion concentration is going to be the same as the sodium hydroxide concentration, so 0.65. And so what we need to do is 1 times 10 to the minus 14 is equal to H plus multiplied by 0.65. And so that means that the hydrogen ion concentration is 1 times 10 to the minus 14 divided by 0.65, which gives us a value of 1.5 times 10 to the minus 14. Then when we negative log this hydrogen ion concentration, we get 13.81 as our pH. And this works the same even if we've got a base that's got 2 hydroxide ion concentrations present. For instance, what is the pH of a 0.8 moles per decimeter cubed concentration of barium hydroxide? So first of all, we need to, again, recognise that it's a strong base, so that means that this will fully ionize, but this time for every 1 mole of barium hydroxide, there will be 2 moles of hydroxide, which means that the hydroxide ion concentration will be 1.6. And so the Kw divided by this hydroxide ion concentration gives us a hydrogen ion concentration of 6.25 times 10 to the minus 15, and then the negative log of this value gives us 14.20. The term POH doesn't normally appear on A-level syllabuses, but it can make your lives easier if you're confident with your maths to use the term POH. As a quick derivation, at 298 Kelvin, as we know, Kw is equal to hydrogen ion concentration multiplied by the hydroxide ion concentration. If we take negative logs of both sides of this expression, we get the negative log of Kw is equal to the negative log of H plus the negative log of hydroxide ion concentration. Now we know that the negative log of Kw is going to give us a value of 14 because Kw is 1 times 10 to the minus 14 at 298 Kelvin. The negative log of the hydrogen ion concentration is pH. The negative log of the hydroxide ion concentration is something called pOH. And so this gives us a really useful term of 14 is equal to pH plus pOH. Now, since pOH is negative log of the hydroxide ion concentration, what you can do is you can take a hydroxide ion concentration, you can take the negative log of it to get the pOH, and then you can subtract this pOH away from 14, and this gives you a value for the pH. And so, for instance, if we had a hydroxide ion concentration of 2.6, we can take the pOH of that gives us a negative log of 2.6. That gives us a pOH of minus 0.41. And then we can work out what the pH would be by doing 14 minus 0.41, which gives us 14.41 as the pH of this solution. This is quite a bit faster, but some people will prefer the KW method. Adding water to a solution will reduce the ion concentration, whether it's an acid or a base, and therefore the pH will change as a result of this. And so if you add water to an acid, the hydrogen ion concentration will decrease and the pH will increase. In other words, the solution will be less acidic. If you add water to a base, the hydroxide ion concentration will decrease, and therefore the pH will also decrease, and the solution will be less basic. This usually comes up in the context of strong acids, and that's where I'll focus for my example here, but it could be applied to other types of solution. An example question might be, what is the pH change if 20 cm cubed of 0.1 moles per decimeter cubed hydrochloric acid has 30 centimeters cubed of water added to it? Since we're being asked to work out a change, we need to know what the pH starts at. We're working with hydrochloric acid, which is a strong acid, therefore it will fully ionize in solution, and therefore the hydrogen ion concentration will be the same as the hydrochloric acid concentration, and so it will be 0.1. And pH is the negative log of the hydrogen ion concentration, and so this gives us a starting pH of 1.00 to 2 decimal points. We've added water to this hydrochloric acid solution, but this will not change the moles of hydrochloric acid present, since water is neither acidic nor basic. And so we can work out the moles that we have of hydrochloric acid by using moles equals concentration multiplied by volume, and so moles will be 0.1 multiplied by 20 divided by 1000, since volume needs to be in dm cubed. And so this gives us 2 times 10 to the minus 3 moles of hydrochloric acid before we added water, and this is still going to be the case after dilution. It's just that these moles will be dispersed over a larger volume of solution, because the new volume has increased to 50 cm cubed since we've added 30 cm cubed of water to our initial 20 cm cubed. And more usefully, we can say that this new diluted volume is 0.05 decimeters cubed. And so then we can work out the new hydrochloric acid concentration by doing moles divided by volume. So 2 times 10 to the minus 3 divided by 0.05 gives us a new diluted concentration of 0.04 moles per decimeter cubed. Hydrochloric acid is still a strong acid, it's just more dilute than before, so we can still say that the hydrogen ion concentration is the same as the hydrochloric acid concentration, and so we can work out the pH by doing the negative log of 0.04, and this gives us a pH of 1.40 to 2 decimal points. The question asked us for a pH change, and so the pH is changing from 1.00 to 1.40, and so this is a change of 0.40. Acid dissociation constants are given the symbol Ka, and they are numbers used to describe the strength of an acid in an acid-base equilibrium. In general, the stronger the acid is, the larger its Ka value will be. These values are based on the dissociation of the acid from the undissociated or unionized form into a proton and a conjugate base. In general, this dissociation can be represented by the equilibrium that I'm showing here, where I've got HA on the left-hand side, which is the undissociated acid, and on the other side of the equilibrium, we've got the proton, and I'm showing you this as A-, and this is the conjugate base. Sometimes it might be preferred to use HX and X- for the undissociated acid and its conjugate base, but typically HA is used. Some examples of Ka values, just to be representative, are for hydrochloric acid, 1 × 10⁷ moles per decimeter cubed. And since hydrochloric acid is a strong acid, we would expect a big number here. And for ethanoic acid, which we know is a weak acid, the Ka value is much smaller, as 1.7 × 10⁻⁵ moles per decimeter cubed. And in general, for monoprotic acid, the units for Ka are always going to be moles per decimeter cubed. You need to be able to write the expression for the equilibrium constant for a weak acid, and I'm going to show you how to do that here. First of all, if we consider the equilibrium where a generic acid, HA, reacts with water, we produce the hydronium ion and the conjugate base, represented by A-. The Kc for this expression would be expressed like this. We always have the product concentrations on the top and then multiplied together, and the reactant concentrations go on the bottom, again multiplied together. Now, to work towards the Ka expression, we need to recognize a number of assumptions. First of all, we're working with a weak acid. So this means that the water molecules are in a vast excess and they are only slightly ionized. And so that means that the water concentration will be approximately constant when compared with the water concentration before equilibrium was reached. And since the water concentration is constant, that means that we can move it up onto the left-hand side next to the Kc expression, and we can combine those together to produce one constant, which we call Ka. And then for simplicity, we replace the hydronium ion with H+. And so where we had the concentration of the hydronium ion on the top of the expression, we now have the H+ ion instead. And this is universally understood as the proton, regardless of its association with water, and it avoids unnecessary complexity in equations without changing their meaning. So the acid dissociation equilibrium is simplified down to the undissociated acid itself on the left-hand side and the hydrogen ion, or we might say the proton, and the conjugate base on the right-hand side. And so the Ka expression for this would be the hydrogen ion concentration multiplied by the A- concentration on the top and the undissociated acid concentration on the bottom. The second assumption that we need to make is that since we're working with a weak acid, very few acid molecules will dissociate, and so the acid concentration is effectively constant. And that means that the acid concentration that we knew when we made up the solution of the weak acid will be the same as the concentration of that weak acid once equilibrium has been reached, because such a small proportion of this acid has dissociated. And so that means that we can know the concentration of the weak acid and we can know the Ka for this acid, and this allows us to work out the pH at equilibrium. In order to do that, we also need to recognize that we're assuming that this weak acid is totally pure, which means that there are no impurities present, which means that since we have a 1-to-1 ratio of hydrogen ions and the conjugate base, we can say that the hydrogen ion concentration is equivalent to the A- concentration, and so we can actually amalgamate those terms on the top of the expression, and so we can have Ka equals H plus concentration squared divided by the concentration of the undissociated acid. It is really important to note, though, that if you are asked to give the Ka expression for a named acid, you must write the Ka expression in full, not one of these shorthand terms that I'm showing here, and certainly not the calculation aid, which is having the H plus squared term on top of the expression. To calculate the pH for a pure weak acid, we need to recognize the generic equilibrium for the dissociation of this weak acid and then construct the Ka expression. And this gives us Ka equals hydrogen ion concentration multiplied by A minus concentration divided by the undissociated acid concentration. And so to calculate the pH for a weak acid, we only need to know the Ka and the undissociated acid concentration. Remember, if you'd been asked to write the Ka expression for a named acid, you wouldn't use HA, you'd use the formula of that weak acid and of its conjugate base. And then we need to simplify this expression, recognizing that the hydrogen ion concentration is the same as the A minus concentration, and that gives us this simplified Ka expression with the H plus concentration squared on the top. And then we have a choice. We either substitute values in and then rearrange it and solve it, or we rearrange it to then substitute the values in later. If we choose to rearrange it, we get the hydrogen ion concentration squared is equal to Ka multiplied by the acid concentration, and this then gives us the hydrogen ion concentration, which can be found by taking the square root of Ka multiplied by the acid concentration. And then the final step, as with all pH calculations, is to do that pH is the negative log of that hydrogen ion concentration that we've just calculated. Let's take a look at an example now of how to calculate the pH of a weak acid. I'm starting with lactic acid, which has a concentration of 0.01 moles per decimeter cubed and a Ka of 1.287 times 10 to the minus 4 moles per decimeter cubed. The acid dissociation equilibrium shows the lactic acid formula on the left-hand side, and then hydrogen ions on the right-hand side, along with the conjugate base. The first thing I need to do is write the Ka expression, which is what I'm showing here. We have the hydrogen ion concentration and the conjugate base concentration on the top and the lactic acid concentration on the bottom. And then we simplify this expression because H plus concentration is equal to the conjugate base concentration. So that gets me the Ka equals hydrogen ion concentration squared divided by the lactic acid concentration. And then we're going to rearrange this. So I've got the hydrogen ion concentration squared equals Ka multiplied by the acid concentration. So substituting my numbers in, I have 1.287 times 10 to the minus 4 multiplied by 0.01. And so the hydrogen ion concentration squared is 1.287 times 10 to the minus 6. So I then need to square root this value that I've got here, and that gets me a hydrogen ion concentration of 1.13 times 10 to the minus 3 moles per decimeter cubed. And finally, I need to calculate the pH by taking the negative log of this hydrogen ion concentration, and that gets me a value of 2.95 for this pH to 2 decimal points. Values of Ka can be almost anything, from really huge, which means the position of this equilibrium is fully or almost fully to the right-hand side, so the concentrations of the product are huge, the concentrations of the reactants are small, which is why we get this huge Ka value. Or they can be very, very small, which means there is only very little dissociation, and the equilibrium lies significantly to the left-hand side, and that means that the number on the bottom of the Ka expression is very large, and those numbers on the top are very, very small. In the same way that we convert hydrogen ion concentration into pH, we can convert Ka values into pKa values, and this makes the numbers more manageable. And to do this, we show that pKa is equal to the negative log of Ka. And so that means if we have hydrochloric acid's Ka value of 1 times 10 to the 7, the pKa is the negative log of this value, which means the pKa is minus 7. And ethanoic acid's Ka of 1.7 times 10 to the minus 5, therefore the pKa is the negative log of this number, and that means that the pKa is 4.77. Do notice that these numbers for pKa don't have units, just like pH values don't have units. Also notice that the numbers are much more manageable and easier to understand and give meaning to than the really huge or really small Ka values are. They're much easier for us to comprehend. In the same way that you can switch between pH and the hydrogen ion concentration, you can actually calculate the Ka value from a pKa value. And to do that, you use the expression Ka equals 10 to the minus pKa. And so if we had a pKa of 3.75, the Ka would be 10 to the minus 3.75. And that means our Ka would be 1.78 times 10 to the minus 4 moles per decimeter cubed. And so in general, you need to know how to convert between Ka and pKa in either direction. And you also need to know the pattern of acidity, where a stronger acid will have a larger Ka value, but a smaller pKa value.